then we are looking at rho times u dot n dA over the internal control surface. Remember, if u and n vectors are similarly directed or oppositely directed, it controls the sign of this integral, and thereby you get the net mass. So mass out minus mass in, okay, per unit time. So similarly, if you think of d by dt of momentum of the system, that will be same as the d by dt of momentum of the fluid within the control volume plus the net efflux of momentum, where the rate per unit time is built in across the surface of the control volume. Okay, so then what we have is the d by dt of the B of the system, or the property of the system, is d by dt of the property of the fluid within the control volume plus this flux of that property across the surface of the control volume. So essentially, if you want to find, for example, the forces acting on a chunk of fluid, if you remember when we derived our momentum equation in the differential form, we took a rectangular parallelopiped geometry dx by dz. We said it's a Lagrangian element, although infinitesimal, and we said, okay, the momentum or change of momentum of that element as it moves through the flow domain is related to the forces on that one. So if we remember, we did all the force, the free body diagram kind of thing. We took the differential element, we drew the pressure that will create the normal forces. We did the stress tensor, the tau xx, tau xy, and all those things. So it's almost the same thing. So if your B is momentum, so the change of momentum of the system, which is given by the forces acting on this system on the left hand side, on the right hand side, this change of momentum can be evaluated. So if you want to evaluate the change of momentum of that system, which can be infinitesimal, as we have seen in the governing equations in differential form for momentum and energy. However, here we are considering a finite. It's not necessary to be finite, but for the sake of some convenience, we are not restricting ourselves to like infinitesimal volume. So our control volume here can have some finite shape and size that coincides with the system at that initial time. And we are saying that your d by dt of, say, the momentum of the system can be related to d by dt of momentum within the control volume and the flux of momentum across the control volume surface, control surface. Now, this above expression can be written as d by dt of this beta times, so this is just the mass, and this is, remember, this is the connector, this is the property per unit mass. So then, to get B, that property, which, for example, B can be mass or momentum or energy, all you have to do is multiply that corresponding intensive property with the mass, well, in this case, the differential mass element, and then integrate over the entire control volume. So d by dt of BCV can be written as d by dt of volume integral of beta times rho dV, where V here is volume. So dV is elemental volume, plus CS times this expression, which just follows from the above expression. Now, Reynolds transport theorem allows us to bring this d by dt inside this integral, and without the addition or inclusion of any extra term in this next step, given your control volume is stationary and its boundaries are fixed, in geometrically fixed. Otherwise, some extra terms, forcing terms, etc., will need to be added. But however, in whatever we are doing, we are going to assume a fixed control volume with a fixed geometric definition, and hence this, this you can bring the d by dt inside without any, further manipulations. In fact, I think this is the precise statement of Reynolds transport theorem. That is, you can bring the d by dt inside. However, this whole method has been labeled as Reynolds transport theorem in fluid mechanics. So for people, I think, who come from mathematical background, they wonder why this whole thing is called Reynolds transport theorem, when all it really is saying is you can, you go from here to here by if your CV and your CS are fixed in space and of given geometric definition. But nonetheless, you see that the powerful message here is d by dt of a property of the system can be related to d by dt of these within a control volume and the flux of that property across the control volume. Okay, so this is a very useful form because sometimes when your system is moving in space with it's deforming, it's rotating, it's dilating. I mean, many things are happening to the system. It is difficult to work with that flowing chunk of fluid. But what we are saying is by defining a control volume in space, in this case, which coincides with that system at time t, we can actually obtain this rate of change of mass or momentum or energy of that chunk of fluid that is moving through the flow field with deformation and all these things happening. Instead of focusing on that chunk of fluid that is moving and doing all kinds of complicated things, we can shift our attention to what is happening within the control volume with respect to that particular property and what is happening across the surface of that control volume, given into the efflux influx of that property through the surfaces of that control volume. So from a system, we can find the rate of change of mass, momentum or energy of the system by not considering the system anymore, but by just looking at what is happening within the control volume and what is happening across the walls of that control volume. Okay, so the first term here gives you what is happening within the control volume. The second term focuses on what is happening across the surface of the control volume, and that we give that surface a special name CS, which is the control surface. Okay, and if you think of it, this thing is really what this thing is. Okay, so this thing is a more precise definition or description of this thing. Okay, so now we will so we said that B, this B, we were using the word B, saying that B can be mass, momentum or energy, and then beta is the corresponding intensive properties. So mass, momentum, energy, this is mass per unit mass, momentum per unit mass, energy per unit mass. Okay, so that gives beta to be 1, or velocity or specific internal specific energy, depending on whether we are talking about mass, momentum or energy with B. So when B is mass, so this is just because sometimes it is a little easier to when you are doing these things for the first time, this B and beta can become a bit confusing. Of course, once you understand these things, then you might yourself be using B and beta to explain it to others, because it just gives you a precise, like a short way of describing it. So now when B is equal to mass, so by using, so this is the starting point. Okay? So this is what we have seen in the previous portion of our discussion. That is this d by dt of B of the system, where B can be mass or momentum or energy, can be given in terms of something happening within the control volume and something happening across the surfaces of the control volume, of the control surface. Now, specializing this B to mass, we can say then that the d by dt of mass of the system is equal to d by dt of the mass within the control volume plus the mass that is going out minus the mass that is coming into the control volume across its surface per unit time. So you can think of flux, but the problem is the flux term, I think it's per unit time per unit area. So here we are integrating, or rather you can say it's the net outflux or the rate of outflux of mass. Okay, so remember once again, this thing gives you the volume rate out of the surface, or rather out of the volume, control volume multiplied by mass, you get the mass rate that is going out of the surface minus the mass rate at which mass is entering the surface. Well, it's not the same surface. Some portions of the control volume surface mass is escaping. Some portions of the control volume new mass from adjoining area is coming. Okay, so you have to take the right local density, local velocity, local surface normal at that location of the control volume surface that you are calculating this thing, and then integrate over the entire surface of the control volume. Now, what is the d by dt of the mass of the system? Again, d by dt is the capital D by dt is the it is your if you because we are we are looking at the mass of the system at time t, then we are moving to the new location where the mass of where the system has moved. We are looking at its mass there, so it's the capital D by dt. Now that is zero because we talked about a mass of given mass identity, so that's that mass is not changing, so that is zero. It is this first term gives you the accumulation or depletion within the control volume. Now, if we restrict this to a steady problem, that is over time, no mass accumulation or mass depletion is happening within the control volume that we have, then the first term becomes zero. And then the second term, of course, if the first two terms are zero, then this whole thing becomes zero. So this is what we get for the mass conservation equation in the integral form. So if you once again, if you remember what we said was u dot n in some regions will become positive. That is where u and n are similarly directed. It does not need to be exactly directed in the same way, but the component will be the component along n will be in the same direction, because in some cases your component of u which is aligned with n can be in the opposite direction to n. So in some cases your u and n, u dot n will give positive value. In some regions of the control surface, u dot n will give negative value. And the overall integral, when done over the control surface, will give you, what is going out, what is minus whatever is going in. Now, if the left-hand terms are zero, then all we get is m dot out is equal to m dot in. Now you can think about this thing. You can draw the control volume, mark some regions as regions where flow is coming out, some regions where flow from other region is coming into the control volume. And then you can show just from this statement and this statement are equivalent. Okay, so this statement just tells you that m dot out is equal to m dot in. Rate at which mass is coming out of the control surface is same as rate at which mass is coming into the control surface, into the control volume across the control surface. Keep in mind that your control volume, control surfaces are sometimes we choose them intelligently, where you can convert. See, this is a descriptive thing to say, but if you have to really work out some numbers, evaluating this surface integral can be tricky, because you have to know, what is this u vector, what is this n vector at each and every location of the control volume. However, if you are able to choose your control volume wisely, for example, you have flow like this. Of course, you can choose your control volume in whatever way you like, but you will see that the choice of the control volume in some particular ways can really, help you to go from this vector calculus kind of expression to algebraic expressions in a single step. So suppose your blue the blue dots represent the boundaries of the control of a control surface that we have, boundaries of a control volume that we have chosen. Then you see that the unit normals are directed like this, directed like this, directed like that. Okay, on these surfaces. So it is now very easy to at least know what is the direction of my unit normals if you draw it in this way. Now, some problems will allow you to draw, control volumes in a way that will help you convert this kind of a surface integral to some algebraic equations very easily. So here again, if we are considering flow going in from left to right, then there is no velocity in these directions. So you see that then all you have to do is, suppose velocity on this side is u1, velocity on this side is u2. Say density here is rho1, density here is rho2. Now, we said that density does not change in incompressible flow fields, but again, you will see that because this is a course in introductory aerodynamics, so we are not restricted to this, incompressible flow per se. Your density can change. For example, if there is a shock wave sitting somewhere in between, you can have a situation like this. If you have heat addition, you can have something like this. So density is changing, velocity is changing. So what will happen is, see, these surfaces will become zero in terms of this number. So then, if you want to do the control surface integral over this whole control surface, surfaces, say, let us label this as A, B, C, D. So in this game, surfaces AD and surfaces BC will not even participate because they will become zero, because U dot N for these will become sorry, what am I saying? So this is sometimes we make these mistakes because see, this is the surface normal. Okay, the normal direction is all right. Velocity is not in this direction. Okay, velocity here is in this direction. Similarly, velocity is not like this. So n vector is okay. The u vector is directed like that's what I was thinking, that the dot product, how come the dot product becomes the same? So sometimes you can make these kind of mistakes, but I hope you will be able to find the mistake. And so this is the surface normal, however the velocity is directed like this. So the dot product given by the cosine, well, the magnitude of those vectors multiplied by the cosine of the angle between these vectors. So here, for example, on these surfaces, your n is directed outward, u is directed, if you think of flow from left to right, u is also directed like this. Okay, so you see u dot n is a positive number. Here your n is directed like this, towards the left. Your u of a different magnitude than this one is directed from left to right. For this particular problem, okay, it can change from problem to problem. So this becomes negative, this becomes positive. So essentially what happens is you end up with something like okay. So see, this complicated, or rather, something that is, you might wonder that, how to evaluate this thing for the particular choice of these things has become an algebraic expression. Okay, so we will see that something similar can also be done for momentum and energy equations. Okay, now again, I should emphasize that you need to find the direction of the unit normals at those regions, the direction of the velocity vector at those regions. Here we chose the control volume in such a geometric usable geometric shape, where as you see on the top and the bottom walls, my unit normal and my velocity vector are directed in such a way that the dot products become zero. So we don't need to worry about those top and bottom surfaces. And then just the left side and the right side then become relevant. And if you look at the direction of the unit normal and the velocity at that face, some dot products become positive, some dot products become negative, and that resulted in this particular form. So this expression gave this expression for the particular choice of this control volume, etc. It is not always possible to draw a control volume like this, as we will see in our subsequent discussions. For if we see the flow through a convergent divergent nozzle, there also we will use a control volume like this, of course, of a shape that is contoured along with the control with the shape of the nozzle. But there also we will use something like this and say, it's a quasi 1D problem, and then we can still use something like this. So here in particular, A1 and A2 are similar, so rho 1 U1 is equal to rho 2 U2. Of course, you understand that if your rho is not changing, then U1 will become equal to U2. But those are special cases. Okay, if A and U and all those things are same, then this kind of thing can happen. Okay, so the control volume description for the CD nozzle, we will go through it when we come to that particular description. But at this point, we will get into the discussion of the momentum equation. So now, having seen the mass conservation equation in some detail, we will now get into the discussion of the momentum equation. Now, you guys have already looked at momentum equation for the the governing equation for momentum in the integral form, in the differential form, where if you remember, we took that differential element of that nicely defined dx dy dz at 90 degrees starting element, and we said that the capital the material derivative of the momentum of that chunk will be dependent on the forces acting on that chunk. And if you remember, we also did the the stress tensor, we did the body force, we did the pressure force, etc., and we showed what is the net force acting on that chunk. In this case, our control volume is a little finite. That is how we have assumed here. So if you remember again, the starting point for this whole method is we move from the system to the control volume. So this CS is still related to the control volume because it is the control surface, which is nothing but the surface of the control volume. So the integral form gives us a way of relating the system description to the description within and across the control volume. Okay? Within the control volume, across the surface of the control volume. Now, in this case, if my B is momentum, then we can say that rho times velocity times elemental volume integrated over the, well, for the system. Okay. So you can integrate these things over the system. So d by dt of the momentum of the system can be related to d by dt of the momentum of the fluid within the control volume plus the flux of momentum across the walls of the control volume. Okay, so control volume, wall of the control volume. So you see that we are relating the time rate of change of momentum of our system with the time rate of change of momentum within the control volume. Well, time rate of change of fluid within the control volume plus the flux of momentum, or rather the time rate of the efflux of momentum. So again, you can work it out yourself. So u dot n, then rho times u dot n, then u vector times rho times u dot n. So that will give you the sense of the momentum that is leaving the control volume across its surface minus the momentum that is entering the control volume across the control surface per unit time. So essentially the time rate of change, time rate of efflux of momentum across the surface of the control volume. So now this time rate of change of momentum of the system is nothing but the forces acting on the system. Okay, so what are the forces acting on the system? So these are nothing but the forces acting on, see, the system at time t is fully contained within the control volume. So what are the forces on the system? So to find the forces on the system at time t, we can try to find forces acting on the surface of the control volume at time t. So that is nothing but the contribution from the pressure forces on the wall of the control surface. We don't write this explicitly, but viscous forces due to the shear stresses. and then the body forces acting on the mass within the control volume. So once again, the time rate of change of momentum of the system is related on the right hand side with things from based on the control volume and the the walls of the control volume. So from the left side is a system description, right side is a description that uses the control volume and its surface. Now, if you think of this is happening because some forces are acting on it. Momentum of the system is changing with respect to time because some forces are acting on the system. So now, to find the forces acting on the system, go back to time t, and at this point, your system is fully enclosed within the control volume. The boundary of the control system, the boundary of the system is coinciding with this CS, or the boundary of the control volume, which we give the name control surface. So then, to find the force on the system at time t, all you need to do is find the force on the walls of the control volume at time t, because the walls of this control volume at time t is nothing but the walls of the control of the system at time t. So to find the forces that are creating that change of momentum of the system, you have to find the forces acting on the wall of your control volume at time t, forces, body forces acting inside the mass within the control volume, and then these two things can be equated. So this is important concept, that is the force on the system that is creating this dy dt of momentum of the system is nothing but the forces acting on the surface of the control volume at time t is equal to 0, and the forces acting, so this is the body force term, so it includes the so essentially the rho times dv gives you dm, and f is the body force, so body force multiplied by the dm, and then you have to evaluate it over the dms will be, you have to take the dm, which is elemental mass, throughout the control volume, okay, and you have to integrate them, and then you can get the forces acting, and on the right hand side you can get the change of momentum or the time rate of change of momentum of the system by using the control volume description. Now, if we look at the energy equation, okay, so if B is energy, then we will say similarly that, again starting from that description where we go from the system description to the control volume description, or the Lagrangian to the Eulerian description, and in this case our B is energy, so this beta will become specific energy or energy per unit mass, and so what we will have is so the time rate of change of the energy of the system, this thing, is similar to what you saw for momentum. So rho times dv gives you dm, elemental mass. When you multiply it by E naught, or the specific energy, then you get the energy for that dm element, and then you integrate it for the entire system. You get the energy of the system, and then if you want a time derivative, you do d by dt. Now that can be related to the control volume, control surface description. And keep in mind that your just like momentum of the system is changing because of forces applied to the system, which we also saw in the differential form derivation. In this case, the energy of the system, so this capital E naught, is changing because of heat that is given to the system and work that is done by the system or on the system by pressure force, compressive forces, then shaft. So here, work due to pressure, work due to shaft, work due to shear, and the dots are because we are looking at the rate of this thing. So we will continue this discussion in the next class. We will see that the energy equation in this particular form is central to the usage of these things in propulsion applications. And I cannot emphasize this particular slide more. So if you understand this slide properly, then I think you will get a lot of value in understanding, how thrust is generated, how how enthalpy changes inside a combustor. These are parts of internal aerodynamics. Okay, so we will do this thing in the next lecture.